All right, we're going to pick up from where we left off yesterday. I had a lot of fun yesterday getting up to speed with crafting interpreters and getting a rudimentary arithmetic interpreter working with evaluation. So this is where I think uh, things take a bit of a turn and have to influence some more than just have the host language interpret it for you. So now you have to kind of represent internal state a little bit. So I'm excited to do this bit now. I did do a little bit of a refactor from yesterday. Hold on a second, let me just pin this window so that I can see it. There we go. All right. So my refactor now main is actually tiny. That's all of main. And I've put the eval and the print in their own files. I also ended up changing some of the syntax around, making it a little bit more streamlined and pipelined with that. So I can take a program and I can parse eval print. Now, also on the print side, there's a shorthand for if you're immediately just matching on the argument, you can just do function and then do that. So I changed all of those to that style. I did have to change some things around on the eval side to make that work. Previously, eval binop took 3 arguments, but now it just takes 1, which is a tuple of all 3 of them. So that's how I can streamline that. And then the pattern matching ends up being the same because the pattern matching can just strip out the tuple into its constituents. All right, so let's go and take a look at statements and state. All my life, my heart has yearned for a thing I cannot name. The interpreter we have so far feels less like programming a real language, more like punching buttons on a calculator. Yep. So this is where, and I've actually, without actually following a tutorial, I've just kind of played around with making somewhat similar concepts, but never really got past just the interpreting of the arithmetic and such. So programming to me means building up a system out of smaller pieces. We can't do that yet because we have no way to bind a name to some data or a function. We can't compose software without a way to refer to the pieces. To support bindings, our interpreter needs internal state. When you define a variable at the beginning of the program and use it at the end, the interpreter has to hold on to the value of that variable in the meantime. So in this chapter, we will give our interpreter a brain that can not just process, but remember. State and statements go hand in hand. Since statements by definition don't evaluate to its value, they need to do something else to be useful. That something is called a side effect. It could mean producing user-visible output or modifying some state in the interpreter that can be detected later. The latter makes them a great fit for defining variables or other named entities. Here's a side note. You could make a language that treats variable declarations as expressions that both create a binding and produce a value. The only language I know that does this is Tickle. There's actually more. Elixir does this, and Erlang. Scheme seems like a contender, but note that after a let expression is evaluated, the variable it bound is forgotten. The defined syntax is not an expression. So the way that you assign a variable in Elixir and Erlang is with an equals sign, but it's actually called the match operator. And it actually is doing pattern matching. So any valid pattern matching expression you can put on the left side of that, and it is an expression. In this chapter, we'll do all of that. We'll define statements that produce output, print, and create state, var. We'll add expressions to access and assign to variables. Finally, we'll add blocks and local scope. That's a lot of stuff. That's a lot to stuff into one chapter, but we'll chew through it all one bite at a time. So I'm not sure if we'll get through this whole thing in the stream, but hopefully we'll get to a part where we can have a little bit of code added. There we go. Doesn't get too far. Okay. Statements. We start by extending Locke's grammar with statements. They aren't very different from expressions. We start with 2 simplest kind. An expression statement lets you place an expression where a statement is expected. They exist to evaluate expressions that have side effects. You may not notice them, but you can use them all the time in C, Java, and other languages. Anytime you see a function or method call followed by a semicolon, you're looking at an expression statement. Pascal's an outlier. It distinguishes between procedures and functions. Functions return values, but procedures cannot. There is a statement form for calling a procedure, but functions can only be called where an expression is expected. There are no expression statements in Pascal. I kind of like that. A print statement evaluates an expression and displays the results to the user. I admit it's weird to bake printing right into the language instead of making it a library function. Doing so is a concession to the fact that we're building this interpreter one chapter at a time and want to be able to play with it before it's all done. To make print a library function, we'd have to wait until we had all the machinery for defining and calling functions before we could witness any side effects. Okay. New syntax means new grammar rules. In this chapter, we'll finally gain the ability to parse an entire lock script. Since lock is an imperative, dynamically typed language, the top level of script is simply a list of statements. The new rules are: program is a bunch of statements. Statement is made up of expression statements or print statements. An expression statement is any expression terminated by a semicolon. A print statement is print in front of an expression followed by a semicolon. I feel like you could just say print in front of expression statement. Not entirely sure why it's done that way. I will note with only oh, actually I could see why that's the case. Expression statement, print statement. Okay. I will note that with only a modicum, I don't know what that means, of defensiveness, that BASIC and Python have dedicated print statements that are real languages. Granted, Python did remove their print statement in 3.0. Alright, the first rule is now program, which is the starting point for the grammar. It represents a complete lock script or REPL entry. A program is a list of statements followed by the special end of file token. The mandatory end token ensures the parser consumes the entire input and doesn't silently ignore erroneous unconsumed tokens at the end of the script. Right now, statement only has two cases for the two kinds of statements we've described. We'll fill in more later in the chapter and the following ones. The next step is turning this grammar into something we can store in memory, syntax trees. Cool. Syntax. Statement syntax trees. There is no place in the grammar where both an expression and a statement are allowed. The operands of, say, plus are always expressions, never statements. The body of a while loop is always a statement. Since the two syntaxes are disjoint, we don't need a single base class that they all can inherit from. Splitting expressions and statements into separate class hierarchies enables Java compiler to help us find dumb mistakes, like passing a statement to a Java method that expects an expression. That means a new base class for statements. As our elders did before us, we will use the cryptic name statement. With great foresight, I have designed our little AST metaprogramming script in anticipation of this. That's why we passed an expression as a parameter of define AST. Now we add another call to define statement in its subclass. Okay, to run the AST generator script, we hold the resulting statement Java file with the syntax tree classes that we need for expressions, print statements. Don't forget to add the file to our IDE project or makefile, whatever. Alright, so we're not doing this because we're doing this in OCaml. Parsing statements. The parser's parse method that parses and returns a single expression with a temporary hack to get the last chapter up and running. Now that our grammar has the correct starting real program, we can use turn parse into the real deal. Program, we can turn parse into the real deal. Parse is now going to take a list of statements and then add them also statements and then return the whole thing. This parses a series of statements as many as it can find until it hits the end of the input. This is pretty direct translation of the program rule into recursive descent style. We must also chant a minor prayer to the Java verbosity gods since we are using ArrayList now. A program is a list of statements and we parse one of those statements using this method. A little bare bones, but we'll fill it in with more statement types later. We determine which specific statement rule is matched by looking at the current token. A print token means it's obviously a print statement. If the next token doesn't look like any known kind of statement, we can assume it must be an expression statement. That's the typical final fall-through case when parsing a statement, since it's hard to proactively recognize an expression from its first token. Each statement kind of gets its own method. First, print. Since we already matched and consumed the print token itself, we don't need to do that here. We parse a subsequent expression, consume the terminating semicolon, and emit the syntax tree. If we didn't match a print statement, we'd have one of these. Okay. Executing. We're running through the previous couples of chapters in microcosm, working our way through the front end. Our parser can now produce the statements and text trees. So next, the final step is to interpret them. As in expressions, we use a visitor pattern. We have a new visitor interface, statement of visitor, to implement since statements can have their own base class. Okay. Unlike expressions, statements produce no value, so the return type of the visit method is void, not object. We have two statement types, and we need a visit method for each. The easiest is expression statements. We evaluate the inner expression using our existing evaluate method and discard the value. Then we return null Java. Then we return null. Java requires that to satisfy the special capitalized void return type. Weird, but what can you do? The print statement's visit method isn't much different. Before discarding the expression's value, we convert it to a string using the stringify method we introduced in the last chapter and then dump it to standard out. Our interpreter is able to visit statements now, but we have some work to do to review them to it. First, modify the old interpreter method in the interpreter class to accept a list of statements, in other words, a program. Okay. That's a statement analog to a value method we have for expressions. Okay. At this point, we're sketching out a little lox program in a text file to run it as a script, something like this. It almost looks like a real program. Note the REPL2 now requires you to enter a full statement instead of simple expression. Don't forget your semicolons. All right, so now what I want to do is let's put a new file here and call it test.lox. Okay, and our goal will be to get this to print out that stuff there. Now I got to figure out how to read from a file in OCaml, and then we're going to parse an eval, and then we'll add the stuff to print it. Now we're no longer going to be doing that print there. And then eval, instead of returning expression, I actually just want to return nothing, return unit. So let's see. Let's figure out how to OCaml read file. Reading text files wasn't as straightforward as with the many other programming languages. To give you some point of reference, here's how easy it is to do in Ruby. Here in Clojure, it's about the same. Basically, there are three common operators when dealing with text files: reading the whole contents as a single string, reading the whole contents as a collection of lines, reading and then processing lines one by one, useful when dealing with large files. When I had to play with files in OCaml for the first time, I did some digging around and noticed that many people were either rolling out their own readlines function based on the built-in input line function or using Jane Street's base library. Such basic operations are not covered in the standard library. It turns out, however, this situation has changed recently with OCaml 4.14 with the introduction of model in channel. While you still need to roll your own read file and read lines functions, the implementation is slightly simpler than before. Even more importantly, the code is now more reliable, as noted by Daniel Bunzel. Okay, let's see. Update. All right, so this is read the entire file. And we'll call that test.lox. Okay. So there's test file. We'll call that test file. And now we want to parse it. Test file is a string. Do test file and Now I gotta change our eval and our parse. Okay, so let's go back to the grammar listed up here. Program is now a bunch of statements and then an end file. So let's go to our parser. So previously program was just an expression and end file. Now it's actually going to be a bunch of statements. So first of all, let's make a statement is, well, that's kind of cool. Statement is either an expression statement or a print statement. Expression followed by semicolon. I don't know why it has two of these. So we could separate expression statement and print statement out into their own definitions, but I think that's good enough there. And now, now a program is made up of any number of statements followed by an end of file. Now in our Elixir, we're already grabbing print as a token. All right, so now we just got to figure out how to do multiple statements. So that's not what we want yet. How do we do this? How do we say any number of statements? All right. Let's do. All right, I gotta run for a sec. All right, I'm back. So I was just about to research how to do a list of statements in, I forgot what I'm actually using um, in OCaml. Let's see. This Dune file should tell me. OCamlX is the lexer. The parser is called menher. Okay. So OCaml menher list of statements. I don't know if that's gonna return back anything. Actually, that looks promising right there. Since there's no marker for a group of functions, you have to declare your list yourself with several constructors. Dex non-empty list, dex no function, hdex tl dex, head tail dex same as yours without functions. Let's see. I don't really want to read the whole reference there. Okay, let's see what we want to do here. Let's see if there's like a cheat sheet for men here. Okay. Once that's in place, we can start specifying the productions, and then here the productions are organized into rules. Each rule lists all the possible productions of a non-terminal symbol. Here, for example, is a rule for program. Either end of file or a value, some value. What is a separated list thing? It also uses a separate list to parse both JSON objects and lists with one rule. So I did see that one, like a plus in front of it. That doesn't look like it would help me. So I'm curious about this token is equal to parse new line blank plus. It's been a while since I've actually tackled building this parser. So I don't remember how to do it correctly. Not sure what that will do. Here we're just going to print as well for now, and our test file we're actually just going to just have a single one for now. Okay. Let's see where we are right now. Unbound constructor print. Parser MLY unbound constructor print. Okay. I need to actually have that print in. Is it my Lexer? Or the AST? AST, that's what it is. Okay, so the AST now has to have where did I define bind up? Oh, expression is one of those things. Okay. A statement is now either a statement expression or an expression statement or a print statement. Okay, let me think about how to do this. Expression here, this bit right here, corresponds to, does that correspond to that expression there? Literal, not exactly. I guess it's because I haven't gotten to identifiers and such yet. Right. So we're not really doing identifiers or controls right now. So these four do align up with those four there. Okay. So I'll leave them in there, that's fine. So an expression used to be program was a single expression followed by end of file. Now it's a list of statements. So I now need another thing called type program, which is a list of, and actually it's going to be a list of statements. So I need a type of statement. Type statement equals expression statement or a print statement of expression. Maybe these have to be defined afterwards. Okay. Now we need to do type program of list of statements. Okay. That looks right to me. So now we need this one to be Do I need that to be an expression statement? Can this be just be expression? No. Okay, so we're gonna put we're gonna put expression statement in front of that, and this will be print statement. Okay. And now that will be a list of statements. Cool. I have no idea if that's correct or not, but let's try running this. Unbound value expression. Did you mean exp? On parser MLY, line 60. Okay. I need to do E is equal to that, E is equal to that, and then put E there instead. The expression is type statement list, but an expression was expected of type statement. On line 55. The expression is type statement list, but an expression was expected of type statement. What if I just make that S? Nope, doesn't like that. Let me clear this out for a sec. The expression is type statement list, but an expression was expected of type expression. Let's say we only want to handle a single statement for now. Expression was expected of type expression. Why is that the case? Because we said the root is expression. That's why. So instead, let's make the root program. The expression is type statement, but expression was expected of type program. There we go. So now we can make this list of S. No, that's not going to work either. The expression is type AST program, but the expression with respect to AST expression. Okay. We're getting there though. We're getting there. So now we're having an issue at parser. This expression has type AST program, but an expression is expected of type AST expression. Lexer. Let's see where AST is being used here. Just there. Okay, AST program. And then where do we have, got a parser, and then the next thing parser goes into is the evaluator. All right, what was the error again? Test file parse. This expression is type AST program, but an expression was expected of type AST.expression. I'm going to delete the build folder and rebuild it. Okay, so it is still an issue. Expression is type AST program, and expression was expected of type AST expression. So parse is expecting AST.expression. We have AST program there. This expression has type statement list, but an expression was expected of type program. Now a program is a list of statements. So if I do this, I'm trying to figure out where it's expecting type AST.expression. Because we've told it explicitly that the start is program. Line 9, characters 9 through 27. Okay. Okay, so can't find test.logs. No such file or directory. Don't know where it's searching from. Let's try putting it in the root, maybe, and see if we can find it there. Hey, there we go. Okay. All right. So nothing wrong with doing that. Now if we try and put it into parse, Ah, okay, you know what? I think I'm already seeing something. Okay, do that. Expression is type AST program. The expression was expected type unit. Okay, AST program. Ah, okay. So now we're taking the AST program and then we're saying parse and then eval and then print. And then the error now is this eval was expecting an AST.expression. That's what it is. Okay, so now we need to say eval, this will be eval expression, and we're going to do a eval for the actual statements then, for the program. Let eval equal function, let's see, we want to loop through and evaluate each one of the statements. So let's see, OCaml loop. For loops and while loops. Okay. By the limited form of the familiar for loop, for variable start to end value to expression. Okay, so we can just say equals function, and eval is going to be either, if it's given a list of, let's see, if it's a statement, if it's a program, I just want it to loop over it and say equals for looping over lists. That's what I want to do. Something like that. Let flm equals oh, okay. That's actually a function there. That's why that's called that. lm there is a statement. Statement. So for each one of them, we want to evaluate the statement. So now we got to do an eval. Let eval statement equals function, and if it's a expression statement, I really should just shorten that to expression statement like that. Let's go to the AST and change that there, and change it in the parser. Okay. Expression, then we want to eval expression. Otherwise, if it's a print statement, then we want to print it and then so we actually want to, when evaluating the expression, we want to end up returning not back another expression, but then just unit. So for now, what I'm going to do is I'm actually just going to return unit. And when we print statement it, we're going to we're going to print it out, and so let's open print, and we're going to say print the print E. There we go. Okay, what does this not like? Unbound constructor expression statement. I think I need a rebuild to get an update for that one. Unbound constructor expression statement. Was AST updated? AST was updated. Parser's updated. Anywhere else that needs to be updated? I don't think so. Okay. Now when we eval the program, let's finally do that. Eval the program, we're just going to, for each one of them, eval statement. So list.iter let f statement, I think we can just say list.iter eval statement. And I don't even think we need the program bit. Okay, I think we have an eval that's correct now. So now we then eval, and then we don't even print anymore, because eval should be returning units at this point. Okay, so now we have expression is type AST program, but an expression is expected to type AST statement list. Ooh. So we're getting really close. Now the problem is that this is producing a statement list. And even though program is defined in the AST as a statement list, statement list, is that a thing? unbound constructor list. This expression has type statement, but an expression with respect to a type program equals statement list. Okay, we're regressing a little bit. I think that was fine. List a statement. So we're just playing with types here now. I think semantically it's there. It just needs to figure out AST statement list. Okay, so let's think about this. Expression is type AST program. So parse is actually returning back an AST program. But the eval is expecting a type of AST.statement list. Well, if program is a statement list, statement unit. This one takes a statement list and produces, okay, I see. I see. So this guy's expecting a statement list. Or end of file. Maybe that's what I can do. Maybe I can wrap the or end of file into it. No, I don't think so. Program is a list of statements. So we tried that one. Then it says constructor. So then we tried this. Did we try that? Ooh. We got a little further here. This one's not using print anymore. Wow, look at that. All right, we got there. That took a while, but it's mostly just appeasing the type system here. So let's figure out what actually happened here. This plus is getting multiple statements, and then just doing S there is already a statement list. In the AST, it's defined as a statement list, and then here eval is expecting a list of statements, and then evaluates each one of them. For expressions, right now I'm not even evaluating it. I suppose for completeness, we could say eval expression E and then return back unit. Grab the E from there. I think that works? Nope. This expression is type expression, but an expression was expected of type unit because it's the left-hand side of a sequence. Expression. This expression is type expression, but an expression was expected of type unit because it is in the left-hand side of a sequence. I thought that's what I'm returning the unit for. Okay. Let's just return back the unit for now. Okay. So let's see if it can actually do multiple. Let's see if it can actually do, 1 second. Parse y, let's see. Eval. I'm printing the printing the expression. I need to evaluate the expression first. So eval expression, and then print. There we go. That's what I want to do. Okay. So let's go back to here, and they had this test one, and we're going to see if it can do that. Oops, let's go back to test blocks. 1, true, 3. I wonder if that was intentionally a pun like that. 1, true, 3. That's pretty cool. I suppose we actually wanted to, when printing, put a line break in there. We can make it so that print actually puts a yeah, sure. Yeah, that's okay. We'll leave it as it is for now. Cool. All right, so we have now, instead of a program being an expression, a program is now a list of statements, and they're evaluated one at a time, sequentially top to bottom. Awesome. All right. So I'm going to do a little bit more cleanup, and maybe make it a little bit further, but I'm going to stop the stream from now and pick it up in a little bit.